Okay. Well, today I will discuss this. The title of the talk is the skein value mirror of the topological vertex. And it's about a paper I wrote of the same title with Tobias Ekholm and Pietro Longhi. And you can find this paper on the archive. So, to begin with, what is the topological vertex? Introduced in a paper by Mina Albert Clem, Marcos Mourinho, and Kumran Vafa more than 20 years ago. And at the level of formulas, so there's a formula. Okay, first of all, before the formula, what is it? It's something which takes as an input, just at the level of formulas, something which takes as an input three partitions. And we're always going to draw partitions as this kind of thing. So it has some amount of boxes. Whatever. And it gives you out some Q series. And this Q series has a formula. And the formula, I'm going to write it. It's Q. So Q series is an element of Q to the some power times Z power series in Q. And it has a formula, Q to the kappa lambda 2 over 2 plus kappa. This formula didn't appear in it's a close relative of the formula in the original paper. It appeared in a bit later paper. Times some kind of Schur function. Schur function is some combinatorial object associated to a partition. The trace, some kind of character of some corresponding representation of the symmetric group. And then a sum over S. And some kind of expression in skew Schur functions. Skew Schur functions are something you can define in terms of the Schur functions. So this expression where kappa lambda, let's put it over 2, is the sum over coordinates ij in lambda, where like if you put that on the upper top quadrant, j minus I. So this is like what's called the total content of the partition, and this rho is so a Schur function. You input into it kind of a infinite sequence of numbers, and this rho is q minus 1/2, minus 3/2, minus 5/2, and so on. And so this means that into this guy, I put the infinite sequence of numbers q to the minus 1/2, q to the minus 3/2, q to the minus 5/2. And this means into this guy, I take the partition, I kind of read its parts. So this one would say 6, 5, 3, 2, 1, 1. I put a bunch of zeros after that. I add this number, and then take q to that. That's some infinite sequence. Okay, so That's some formula. And I write this formula for two reasons. I'll use it later on, and also, it's some non-trivial formula. It's okay. But these people are some kind of physicists, and so they wrote this formula for a reason. And the reason is that this is supposed to count. It's supposed to be like something in string theory, but it's supposed to count basically holomorphic curves in C3, ending on a certain configuration of Lagrangians. So this was the original AKMV configuration of Lagrangians. In terms of this kind of like toric diagrams, I draw something like this. Yeah, and they use it as some building block for computing open string theory in toric Calabi-Yau. Let me mention also the derivation of this formula is it's kind of derived. Those guys derive it by some kind of arguments about the relation, ultimately about the relationship about the open string and the Chern-Simons theory. So I never entirely understood. Is it derived from that, or like motivated by that? Or derived? All right. So sometime after that, yeah, partition. So this means this means eta is a partition. This term is 0 unless eta sits inside lambda 3 transpose. And if it sits inside lambda 3 transpose, I delete it, and I've got some kind of skew shape. Like for example, eta might look like this, okay? And then you delete it, and you have this kind of skew shape, the difference, and there's something called a skew Schur function, which you then evaluate at this number. And the skew Schur function, whatever it is, it has some expression in terms of usual Schur functions. Yeah. It's like the character of the representation of the infinite symmetric group with that. Whatever, it's some combinatorial thing. Okay. So yeah, I was saying, so shortly after this, but still 20 years ago, there's a paper of Akunkov, Rashtikin, and Bafa who explain that this this thing, it's not only about string theory, it's about something which people could have considered at least 1 century ago and perhaps longer ago. This expression, I'm going to give it a name. Let's call it C lambda 1, lambda 2, lambda 3. That's this formula. There's a big formula. So these guys, they show that the C lambda 1, lambda 2, lambda 3, it is also the appropriately normalized count of, so there, this kind of tripod picture was about the image of C3 under the moment map, under a moment map. Here, this tripod, it's supposed to be a picture of the corner of the room. And in the corner of the room, you can stack boxes, so like boxes. Okay, and then, so on. And so maybe a century ago, already, maybe even before that, people were interested in how many such configurations of boxes there were for a given finite number of boxes. So you can ask for, you can form the sum over n number of such box configurations with n boxes times cube the n. And this is given by this famous McMahon formula, which, and hopefully I remember, it's a product over 1 over n, 1 minus cube the n, again. So this is some kind of old story in combinatorics. And this thing may show it is the appropriately normalized count. This counts kind of box configurations with asymptotics. So like now, instead of a finite box configuration, you let the boxes go off forever, and you require that eventually they become just this picture times a line. Okay, so along these three legs, they eventually become that partition times a line, sort of asymptotics. Lambda 1, lambda 2, lambda 3. So it counts this. So you form some kind of Q series counting these. Of course, you can't take Q to the total number of boxes because there's infinitely many boxes. You have to normalize it somehow. And so you do that, and then you divide by this function. So you divide by the boxes with kind of zero asymptotics, and that's this same formula. I mean, that's the formula. So in other words, okay, let's say it precisely. If you write sum Q to lambda C lambda 1, lambda 2, lambda 3, Q lambda 1 plus lambda 2 plus lambda 3, this equals this kind of normalized box count sum count with asymptotics lambda 1, lambda 2, lambda 3, Q, how to say, Q this appropriately normalized thing divided by this McMahon. Okay, so this could have discussed this in the 19th century. So that's some here, sum over, I don't know, lambda 1, lambda 2, lambda 3. Oh, no, you definitely don't do that. What? Why not? Yeah, I sum over all asymptotes. I mean, it's this whole sum, which is equal to the whole sum divided by. Oh, I guess you could do it term by term also. Yeah, you could do also term by term. Okay. Oh, yeah. No, of course you're right. Yeah, sorry. I'm going to sum over the lambdas in a second. Yeah. Of course you're right. I'll sum over the lambdas in a second. Okay, and then the only other thing I want to say about the history of this thing is that shortly after this kind of proposal, so this original proposal was about counting open curves, but at the time in the subject in mathematics, people only knew how to define counts of closed curves. And there's a way to translate predictions about open curve counts into closed curve counts involving the relative closed Gromov-Witten theory, relative closed Gromov-Witten theory. So this implies a prediction of a different count, a slightly different count given by the same formula in the relative closed Gromov-Witten theory, which was proven by this kind of work of there's this kind of two groups involved in this. There's one Malik. There's kind of two works in this series. There's this Malik, Nekrasov, Akunkov, Pandey work, and plus a work by similar authors where Nekrasov is replaced by Oblomkov. And then there's another work by Jun Li, Melissa Liu, Keifeng Liu, and Jian Zhou. So these people proved mathematically that indeed this formula governs the closed relative Gromov-Witten theory in C3 relative certain divisors. Okay, so that's the history. That's some brief review of the history of this subject from this original work of Mina and company was more than 20 years ago, and those mathematical works were, I don't know, like 15 years ago. So it's been a long time. So then you could ask, why am I talking about this subject now so many years later? One reason is that, as I said, at the time, the open Gromov-Witten theory, any kind of open curve counting was not yet mathematically defined, but recently we've defined it. And so one can ask, can you prove that this formula from long ago gives the same kind of, is correct, or that we can also prove it in this actual open curve counting. And if all I was going to tell you is that in this new theory, in this kind of new theory, you prove it the same way as in the old theory, then I wouldn't bother giving this talk. But in this new theory, which I will review for you in a second, the methods of the old theory are no longer available. So all these works, the basic strategy is you have some moduli space, you use something called equivariant localization to reduce the problem to a problem of combinatorics, then you do the combinatorics problem. That's the basic strategy of these old works. And in the approach to open Gromov-Witten theory, because of the way we set up the subject, that approach is not available. I'll explain to you why when I review the setup of that subject. And as a consequence, we needed new methods, and those new methods, actually, they turn out to be much easier than the old methods. And then moreover, the nature of the new methods, so this old kind of result, basically they found and calculated every curve. That's how it works. Like, look at the whole moduli space, look at all the fixed points, you count them all. In this new method, I will count I don't know, like 6 curves, and prove they determine the rest. So that's some kind of historical introduction, which you can. And at the moment, no. We would need, but no, just because we haven't looked at it. I mean, maybe let me rephrase your question as asking you guys. The reason you studied this in the first place was that so then you could like put them together and so on. And we haven't started thinking about that part yet. It obviously works. We just haven't. Okay, I'll keep this formula for a bit. This one? Lagrangian. Yeah. I'll review what Lagrangian is. That was some kind of history, and now let me now. So before I get to the geometry, let me state a purely combinatorial result, which it may also be new. So the theorem. Before the theorem, I should have said something else about this formula, which is, so this formula, it is not obviously symmetric between lambda 1, lambda 2, lambda 3. They play different roles. But the statement that it's this kind of box counting implies, so this C, lambda 1, lambda 2, lambda 3, it implies a cyclic symmetry by kind of rotating the room. And the box counting statement also implies what I'm about to say, but you can see more easily just from the formula, which is this C lambda 1, lambda 2, lambda 3 is Q to this sum kappa lambda I over 2 times C lambda 3 transpose lambda 2 transpose lambda 1 transpose. That corresponds to reflecting the room along some plane. So these are the symmetries of this function. And so the kind of the purely combinatorial statement is the following. It's the theorem. The relations S box Q lambda 2 transpose plus rho times T lambda 1 lambda 2 lambda 3 equals sum alpha I alpha 1 in lambda 1 minus box T alpha 1 lambda 2 lambda 3 minus sum gamma 3 in lambda 3 plus box Q for the kappa gamma 3 minus kappa lambda 3 over 2 T lambda 1 lambda 2 gamma 3. So here's some relation. So there's 6 of these relations, but you can get them all from this one by applying those symmetries, plus 5 more from symmetry above. Have a unique, up to scalar multiple, I'll say it this way, unique solution with T empty, empty, empty equals 1. And the solution is T lambda 1, lambda 2, lambda 3 equals minus 1. So it's basically this C, but some slight, with a different sign and a different, and with some transposes. It's not important, this difference between this T and this C, but just to write something correct. I mean, of course, you could have just messed around with the recursion a little bit, so there's a recursion from this one instead. But that's the statement. It's that this this formula determined by this recursion. And to study, so maybe I'll say a little bit about why that's true. But so basically what I have to tell you today is maybe two things. One, why this formula is determined by this recursion. I'll explain a little bit. And then the maybe more interesting part is going to be how this recursion comes from geometry. But I wanted to, you know, once I've explained to you those two things, it will be a derivation of why this topological vertex is indeed the curve count of in C3 with these Lagrangians. What are you starting over? Yeah, so this means that gamma 3 is a partition of the form lambda 3 with one more box. Anywhere. Well, I mean, you know. There's a finite sum. Yeah, finite sum, yeah. Oh. Yeah. So like, for example, if gamma 3, if you have a partition like this, then, you know, you can add boxes here, 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 or here. That would be a sum over 4 terms.
So we wrote the recursion formula in this later paper.
Yeah.
It's got to be this formula. It's exactly
yeah.
the same structure. It's written
okay.
in different bases, not in base letter representation, but like it's short while little bases. But we should compare.
Yes, I agree. But I thought you have somehow like infinitely many recursions or something. So is this one of them or all of them, or like how is it related?
I think they're generated by essentially one.
Okay.
Like
Great. Let's check. So I want to explain a bit. So I won't torture you for too long about this, but I want to explain because it's very short. In fact, the proof that of this theorem. Well, just kind of outline it. Mostly, I want to show you how short it is. That's the main thing I want to show. So the proof of this theorem has two parts. I should first of all tell you that these relations hold for this guy, and then second of all, they determine it uniquely. So let me first show you that they hold. Yeah, I have to keep both the relation and the series. Lemma. So for any, I won't prove this lemma. It's a fact about skew Schur functions. You can check it yourself. For any lambda mu, you have this identity. The sum over eta. All these Greek letters always partitions. Sum over tau in eta plus one box, but no, minus a box as lambda over mu x as mu over tau y equals sum eta sum alpha and lambda minus one box as alpha over eta x as mu over eta. That is supposed to be an eta y. Okay, and so what is different on the two sides here? This lambda turned into an alpha, which I sum over, and this this eta, this tau turned into an eta, and this alpha is somehow 1 smaller than lambda, and this tau is 1 smaller than eta. Okay, some kind of exchange of who gets raised and who gets lowered. And the basic reason why it's true, if you check, so you check this, you check this identity by just plugging in the rule for raising or lowering by 1 a partition, and the rule is that to raise or lower, you just sum over all the ones that are 1 bigger or 1 smaller. You just plug that in and check, yeah, it's true. Okay, so that's some lemma. And then, okay, well, I'll use this part. And then the next lemma is that sum eta lambda over eta as 1 box. 1 box means the partition whose diagram is 1 box. As 1 box y as mu over eta y equals beta mu plus 1 box sum mu as lambda over eta x as beta or eta y minus sum alpha in lambda minus a box sum eta as alpha over eta x as mu over eta y. Okay, yeah, some big formula. And the proof of this formula is that there's something called the skew-Pierre rule. It's like the Pierre rule except for skew shapes. And the skew-Pierre rule says that S box. So the skew-Pierre rule is kind of the key to deriving this recursion. And so it says S box S mu over eta y equals a sum over beta and mu plus box as beta over eta y minus. So basically, okay, maybe I finish writing it and I tell you what it says. Sum over tau and eta minus a box as mu over tau. So x and y are just formal variables.
On the left-hand side?
Let's see. Yes. So yeah, of course something here is wrong. Thank you. This one should be an x. Yes. Thanks.
And then in the formula you're writing there, the last one, the skew-Pierre rule.
Yeah.
Last line.
This one.
Yeah.
Always. You want this one to also say y. Yeah, also y. Yeah. So what is the skew-Pierre? So the usual Pierre rule set is about usual sure. Maybe I'll tell you the usual Pierre rule. The usual Pierre rule is for usual sure functions, and it says s box y times s lambda y is a sum over eta is lambda plus a box as eta. That's the usual. This is what's called the Pierre rule, and this is the skew-Pierre rule. It says that for a skew, You want to deal with skew Schur functions. Well, you look at all the ways you can add a box to the bigger one or remove a box from the smaller one. That's the effect of multiplying.
And presumably it just follows straightforwardly with some gymnastics from the actual period rule, right? Because this Schur function is basically a Schur function with some sum from, right?
I think that's more or less true. I think that's true. Some people wrote like a whole paper about this, but I think that's basically true. I mean, somehow this fact did not appear in the literature. Probably people knew it, but as far as I can tell, I mean, someone wrote a paper about this in like, I don't know, 2010 or something. And as far as anyone could tell, it had never previously appeared in the literature. But indeed, the proof is. I mean, they gave a combinatorial proof, in fact, of like moving, the tableau around. But if you want to give just kind of a gymnastics proof, you can do that also. That one's short. Okay, and so there's the skew-Pierre rule, and to derive this formula from the skew-Pierre rule, you multiply. So after this, to derive the formula, you multiply by S lambda over mu at lambda over e to x sum over eta, and then apply first lemma. Okay, so that's it. That gives you this now this lemma. I'll erase now the usual Pierre rule. And then to get a recursion, to get the recursion for the C lambda 1, lambda 2, lambda 3, you take lambda in this formula. You take lambda equals lambda 3 transpose, mu equals lambda 1, y equals q to the lambda 2 transpose plus rho, and x equals q to the lambda 2 plus rho. Okay, and then that, so if you check, that gives you some recursion for the original C's, and okay, for some reason which is you should not pay any attention to whatsoever, you then do again some gymnastics that trade the C's for the T's, for the sign and the transposes and so on. So that's it. That's the proof that this thing annihilates the other thing. One reason I wrote this for two reasons. One is show you that it's short, and the second is to explain that I would prefer an even simpler proof. Because what is this thing saying? This thing is saying that there should be an even more pure thought argument for this. Okay, because this thing is saying something like, if you take a box, I mean, multiplying by S box is about adding a box. So this is something like, if you count all the ways, you can have something with asymptotics lambda 1, lambda 2, lambda 3. If you look at all the ways of adding one box to the partition at the top, then you can compute that, and that's related to all the ways of like taking off a box on one side and adding that box to the other side. So there should be some kind of like three-dimensional jeu de taquin or something. If you like this kind of combinatorial stuff, this formula should have a really beautiful proof, which is not the proof that I wrote.
Well, I hate to say it, but the fact that your proof is so general suggests that also this refined
Yeah, that was the second question. That's the second reason I wrote this proof. And no, well, I mean maybe. So the thing I don't know how, I'm not sure what the refinement of this formula is.
Oh no, so basically
to get to the refined topological vertex, I need to do this sum. I need to know this identity with some kind of parameter. I mean, we can discuss it more later, but it's some kind of parameter like C to the size of lambda minus mu or something. I need some formula like this, and whatever argument I had for this one, I didn't check it. I mean, how to say? It was not immediately obvious it was still true in the refined case. But I didn't spend more than like 30 minutes trying to think about it.
I think it's actually a better question whether stuff in the object has here has such a structure. So because their vertex is a better vertex than defined vertex.
Okay. Okay. Yeah. So
and Nikita is all about not exactly like this.
So
you absolutely have to think about.
So thank you, Mina. Precisely the second reason why I wrote all these formulas was to ask the question, what is the refined version of refined? Basically means you add a certain there's something in the literature called refined topological vertex, and as Mina says, there's like many versions of it, and so there's some kind of question about how do you upgrade this whole story to one variable more, and to this refined vertex. No. No, which one is the old theory? So this original story of Mina and company, it began life, if I understand correctly, about the open string counting. Is that true?
Yeah.
So that's how it began life. But in mathematics, so like there's physics and there's mathematics, and in mathematics, they had not yet succeeded in defining something which was an invariantly defined count of open holomorphic curves, but they could turn, I mean, there's some kind of like some yoga which says how to turn open questions, like certain open questions into closed questions, like closed questions relative to the divisor. And so they did that, and then they counted closed relative to the divisor, and they verified that that recovers this prediction. Yeah, okay, so one thing I wanted to explain was so about this theorem. First part was just why does this operator annihilate its function, and then the second part, which is less calculational, thankfully, is about why there's some kind of additional difference between at least some mathematicians and physicists. This calculation you just saw, probably shortest calculation physicists could imagine, but it's the longest calculation I could tolerate. So.
I was really nervous to be right along the
Yeah, that's right. That was the absolute limit. Yeah. Okay, so. All right. So I wanted to explain now why these recursions determine are enough to determine the thing. And for that, what's important about these recursions is that what does this recursion do? It expresses t lambda 1, lambda 2, lambda 3 in terms of something we lower one side by 1 and raise the other side by 1. Okay, so like at first glance, it is not obvious that the right-hand side is not simpler than the left-hand side because it has more boxes. So it's not clear why this is a recursion. And so like if on the right-hand side it was like lambda 1 minus a box and lambda 3 minus a box, it would be obvious that this recursively determines the thing uniquely if it has a solution, but this formula maybe not quite so obvious. So nevertheless, why is it true? So as I said, there were kind of six such recursion relations. I think these 5 more, and the nature of them is that how to say, for every there's one that does each one of the following things. There's one that kind of that one, it raises lambda 1. This one lowers lambda 1 and it raises lambda 3, and there's another one which raises lambda 1 and lowers lambda 3, and similarly for any for every pair. Like for every pair, there's 2 things you can do, and you have one relation which does those things. So okay, and so the point is that Now, how do we inductively determine these t lambda 1, lambda 2, lambda 3? Well, we begin with this kind of t empty, 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 which is 1. And then, first of all, we start building up the lambda 3 variable. So this t empty, empty, t empty, empty, lambda 3. What I do is I want to consider the operations which lower. So consider the relations which relates which raise lambda 3 and lower lambda 1, or raise lambda 3 and lower lambda 2. Okay, so the point is that the piece of these relations, which is lowering this other part, just annihilates it. There's nowhere I can lower lambda 1 and lambda 2. And the ones which raise lambda 3, I have 2 of them. And then, so now if you want to think about kind of some partitions, suppose inductively I have determined all partitions with, let's say, k rows. And now, when I raise lambda 3, even if I have just even one of these relations, then the value of the thing with one more box will be determined, so the value of the thing with one more box will be determined by the value of the thing with less boxes, plus other things which have only k rows. Okay, so that one's fine. It's determined inductively. And now suppose, and then the next part of the induction is consider the situation where I have kind of k rows. I've determined everything with k rows, and I now consider things with maybe more than one, and I've inductively determined with up to like L boxes here. Okay, so I've determined inductively. Here I did with just one, and suppose inductively I've done up to L. Then the next step is I add one box more, and I can add one box more here, here, or in these places. Okay, so let's put this in different color. Or in these places. Okay, and that gives me 2 undetermined things in terms of stuff that I know. But fortunately, I have 2 relations. And so you need to check that this 2 by 2 matrix is invertible. And you check it, and it is. And therefore, inductively, this is determined by the previous ones. So far, so good. But so then, having done that, that determines now, having done that, that determines now t empty, empty lambda 3. And so now let's determine lambda 2. And to determine lambda 2, I similarly use the ones that raise lambda 2 and lower either lambda 1 or lambda 3. And the argument's the same. Lowering lambda 3 might do something now, but I know everything with every lambda 3 and nothing else. So lowering lambda 3 is okay because I've inductively determined this. And then so that determines t empty lambda 2 lambda 3, and I play the same game for lambda 1. So the basic point is that the basic point of this business is that I have kind of this 2 by 2 system of relations that raise each given partition. Okay, and that proves that this thing kind of inductively determined uniquely. Any questions about that? Okay, great. Maybe I'll wait 1 second longer about questions. So do you recognize this argument?
Yeah, we have to worry about the same thing.
Okay, great. All right. So now we come to the more interesting part of the talk, where I explain to you how these relations show up from some geometry. And first, I better tell you what geometry. And so now we discuss the skein valued curve counting. All right. So what is this about? The setting is I take X, a Calabi-Yau threefold, L in X, a Lagrangian. Strictly speaking, you should say it's Maslov zero. Some grading issue. And we want to count holomorphic maps of the form some surface, its boundary, maps to X, L. That's the job. And there's a this problem mathematically speaking, this problem has the virtue of being an index zero elliptic nonlinear PDE, and therefore its kind of solution space has expected dimension zero. This is roughly the same fact as in the string theory, which tells you that the Calabi-Yau threefold is the right place to do string theory about some ghost number being whatever. So solution space expected dimension zero means you almost have the right to count solutions. There's two problems. One is the word expected. And the other one is that you could have a zero-dimensional space which is infinite. It's like infinitely many points. The infiniteness issue is resolved by some fact in mathematics called Gromov compactness. The issue about this expected dimension zero, so to actually count, or even if you don't want to worry about this kind of technical question about actually counting, to prove invariance under deformation, because physically, I guess, whatever this is supposed to mean, you should believe, because of the properties of this topological A model, that as you deform the complex structure on X, or as you move L around in certain ways, your answer shouldn't change. To think about these questions, so to actually count, you need to perturb the holomorphic curve equation to achieve this expected dimension zero. And if you do this, then you encounter the problem of how do you know whether so maybe you perturb one way and you have like five solutions of five such holomorphic curves. You perturb a different way, you have like 7 or something. How do you know that you get the same number that doesn't depend on your perturbation? That's a question you meet here. Or if you want to prove invariance under deformation, of course, you meet the same kind of question. And the way one thinks about this question is, well, you look at the space, either the deformation parameter or the space of its perturbation. So this is either this perturbation parameter or some other parameter, we'll call it xi. There's some xi0, some xi1. And you consider the moduli space of solutions for all possible C, and that has some, it's some one manifold. It's a one manifold for the same reason that you had expected dimension 0 before, and maybe it looks like this. Okay? Looks like something. And if it's a one manifold without boundary, then the counts on both sides are equal, at least if you count with the appropriate signs. Because the difference between the counts on the two sides is the boundary of a one manifold and therefore 0. So that's the usual argument for invariance of this kind of stuff in this kind of subject, but it relies on this moduli space in one parameter families not having boundary. And for holomorphic curves with boundary, as I will show you in a second, that's not true. You have this moduli space has boundaries everywhere. Okay, this phenomenon can happen. And let me draw you the picture of how that phenomenon happens, which must be familiar to the string theorists because it's just a picture of some breaking.
So the extra boundaries come from if you count curves.
I'm going to draw them right now.
Okay. There's some assumption that it's like you know all the extra boundaries. Here, something there has to fail.
No, in symplectic geometry, you meet these boundaries, and that's why no one studied this question before, because they were afraid of these boundaries. It's the same kind of boundaries Fukaya meets. I'll just draw them. I'll just draw them. Or maybe you're asking why you don't meet them in the closed theory.
No, and the usual should come.
No one ever succeeded in defining those before, for this reason.
I mean, the A infinity stuff.
Yeah, in genus 0 you can define them. So,
the point here is that the higher
well, I'll explain why. Yeah. So let me draw. Maybe first I'll draw this one that Mina is mentioning. So there's the most classical case of this phenomenon looks like this. So any such boundary, it happens because some path on the curve. So how do you describe a codimension 1 phenomenon in moduli space? You describe some function to R, and we'll relate the positive line, and ask where is it 0. And in this case, that function is the length of a certain curve. And so it can happen in a one parameter family that length of some curve goes to 0, and you wind up with this phenomenon. And that's a situation where this boundary, this thing I was just showing, appears over a family. You go find some boundary of the moduli space where it just stops. And this phenomenon here causes the kinds of problem or feature of kind of A infinity. This is responsible for A infinity structures in Floer theory, as studied endlessly by Fukaya and company. And the reason why this picture was understood historically before in a different way than the ones I'm about to draw is that this thing, it breaks into two things of the same kind. And so you can think about inductively canceling this boundary term in terms of terms that you met before. You like separate it into pieces. There's no you can imagine a similar approach to the picture I'm going to draw now, although it's not the one we'll take. So that's one. That's one. So yeah, that's one people thought about before. I mean, there's something similar about what I'll say now, but it's a little different. So here's a similar phenomenon where this kind of trajectory goes to length 0, and the result is this kind of curve. Yeah. And the one basic difference between this scenario and that scenario is that the thing that it degenerated to has different genus. I'm not, so I can maybe discuss at some point what would be the closest relative to this historical approach. But anyway, I'm going to describe something different now. So anyway, this is some boundary in the moduli space, and if you just were to try and define the count by perturbing and counting, you would discover that your count fails to be invariant. So the way we cure this problem, we is me and Tobias, is that it's in some sense similar. We look at this picture, and we say that we in this moduli space, its mathematical meaning is the embedding of a singular curve into the target space. Because the boundary, I didn't say this about this Gromov compactness and so on, but when you do that, this boundary of the moduli space of curves, it consists of curves with nodes and with this curve with nodes. But if you didn't know any of that and you saw this picture, you would think it's something else. You would think it's the image of a smooth cylinder where the boundaries happen to intersect each other just by accident. And the difference between the smooth cylinder and in the embedded singular one is that the map from the smooth cylinder, it deforms freely. And what its deformation looks like is that kind of on one side, it's like this, and on the other side, it's like this. Let me explain the meaning of these pictures. Remember the surface, it's mapping to a 6-manifold, and its boundary is mapping to a 3-manifold. And so this boundary part of the surface, this is living on the 3-manifold, and it traces out some knot, singular knot at this kind of singular moment, but elsewhere smooth knot in the 3-manifold. And this knot is what I mean by these kind of over and under crossings. And of course, at this moment, why is the knot changing? Because at this moment where the boundary embedded like this is a kind of singular like this, then as you vary it, one way it'll vary this way, another way it'll vary that way. Okay, so that's why in this. All right, very good. So this is just a geometric fact that whenever you see this family, you also see this family. That doesn't help you yet, but it just tells you the nature of the problem. But what we do with Tobias is the problem is that this 2 is not equal to this 1. Okay, that's the problem with this curve counter. And the solution is we declare them to be equal. Of course, declaring 2 equals 1 is a great violence. It sets 1 equals 0, and then the place you're counting. So you could do that. You could set 2 equals 1. That would set 1 equals 0, and that would mean that the place you're counting in is the 0 ring, and your count means nothing at all. So we have to do something slightly more subtle than that. And what we do is we set this knot plus this knot equal to this knot. So we count the curves not as numbers, but by their boundary as a knot up to this relation. count curves by class of boundary.
So this is the skein relation in U1.
It's the skein relation. It's the HOMFLY skein relation. I'll write it in a second. No HOMFLY skein. And the skein relation is this. So the HOMFLY is UN, collects UN for all n. And the only thing that's different about this one than this one is I'm counting this guy by a z, and I'm counting him by, I'm allowed to do that because he has different Euler characteristic than he does. So I'll count curves by the class of the boundary in the HOMFLY skein. And the HOMFLY skein has three skein relations, of which I have written the first one, and let me write the other two. And let me explain where the other two come from. I mean, in the similar way. Because the other two.
So in other words, if these boundaries are an object of multiplicity n, then
I make no such. I mean, I don't discuss the multiplicity of the boundary. I don't specify the number of the boundary branes or anything like that. I only work with HOMFLY. I have not specialized.
There's something a little funny, right?
I agree. I agree.
In this, up there, right? You a priori don't know if you're even ending on the. I mean, I could close it in different ways and have like the last term.
Let me explain how these two skein relations arise, and then maybe it will become more clear. Okay. So, another phenomenon where some length shrinks to zero is the length could be the length of the boundary itself. So I draw the red thing as the region. So now, okay. So the red is now in this picture where it intersects. It's both the thing shrinking to zero and where it intersects the Lagrangian. And maybe this time I'll just kind of draw something to indicate the Lagrangian. So this is a kind of family that ends. And like before, so the kind of if you know about moduli spaces and their boundary and so on, then you recognize this thing as a genus 1 curve with a hole, but the hole has circumference 0. Like a strange kind of hole, but it has. If you didn't know about any of that, you would think it was just a closed genus 1 curve which accidentally intersected Lagrangian at one point. And that one has, okay, so let's consider that one. Okay, that again, leads to this point, which is not now a hole. But that one, it doesn't really know the Lagrangian there at all. It just behaves like a closed curve. So it kind of lives its own life. I never know how to draw this last picture. This is a two-dimensional locus. This is a got it wrong. This is a two-dimensional locus. This is a three-dimensional locus. And they're in a six-dimensional space, so you wouldn't expect them to intersect So they intersect accidentally in codimension 1 in a one parameter family, and so you know, generically they miss each other, but they in a one parameter family, things which don't intersect when they pass through an intersecting moment, something has changed. They now avoid each other in different ways, which can be captured by a linking number. So that's why I've drawn different pictures before and after. The topology is different. And okay, so what about this one? Well, again, this has somehow different weather characteristic. We count it by z, and so this starts to look a lot like that second skein relation, but not quite yet because I don't have this a variable. And if I don't introduce anything else, if I just try and leave it like this, then these two sides will be equal because we're counting curves by their boundary, but these things both have no boundary, so they count the same. And I have to fix that, and I should probably fix it to make it look like that. And the way you do it is you use A to record this linking number. That's what's changing, so you make A the linking number. And the way that with Tobias we record this linking number is we choose a forward chain which ends, actually we ask there's going to be two copies of the forward chain. I guess we call it W, and we ask that boundary of W is twice the Lagrangian. And then we count everyone with A, so count by A to the curve, the number of intersections of the curve with W. And so then one of these sides will be A, and the other side will be, they'll differ, these two sides will differ by an A squared because we pass through this thing and changes it, and then you get this second skein relation. So now it's time for your question.
So double is a chain with boundary on twice L.
Yeah. Twice just because I want the difference between A and there should be a squared difference between those things. What? No, I mean, I'm assuming that you can find such a chain. Yeah, so if you change that chain, it will change by some change of variable in A, and whatever variable is counting H2 of the space.
So if I just have, this is supposed to be a completely general story, right?
What is completely general?
The open plus closed.
Yeah.
Theory, whatever, right?
Yeah.
I mean, it seems to have too little data, right? So for example, the choice of flight connection on the Lagrangian that doesn't answer this.
No.
How come?
You want I mean, literally it doesn't. If you want a philosophical answer, it's because what I'm right. What is the skein? The skein is the space of functions on a quantum version of the space of flat connections on the Lagrangian, right? And so I'm taking a value in some universal place, which you could then plug in. You can't really plug in a flat connection, but if there was such a thing as a quantum point in that space, then you could plug it in. Like you can't evaluate a skein on a flat connection, right? You can only evaluate, flat connection is the classical limit, and so yeah.
But you somehow allow to. I mean, I could have different brains with different numbers. Like
each brain gets its own A.
Each brain gets its own, and there's no mix scheme that you'll ever end up.
Let me correct myself. If you can give each brain its own forechain, then each brain can have its own A. But sometimes you can only do this by having a four chain which ends on several, like two different branes. It stretches between them. And in that case, those branes have to share the same A.
Wait, I see.
And from a certain point of view, the thing which really exists, I'm not sure. It's like you take the kind of the theory in just X, and so if I have a theory just in X, and I consider a four cycle, I can bulk the form by that four cycle, just count intersections through it. A different point of view on this discussion is that I'm trying to bulk the form by a four cycle with boundary. And this is the correction needed to do that. So if you try and do that, then you have to incorporate also the kind of open theory of what happens at the boundary of this cycle. I told it from the point of view of wanting to count the open curves, but yeah, you could tell it from the opposite point of view. You could try and count only closed curves, but count them by their intersection with a four cycle of boundary, and then try and make that an invariant theory. And if you did that, you'd be forced into the same thing for the reverse reason.
And the last relation?
Yeah, I'll do it now. So there's a problem with what I just said. And that problem is that if I count these people by their intersection with this four chain, I better also count him by his intersection with the four chain. And for that matter, even if you didn't want to do that, you can have things which, well, anyway, you better do it. And if you do that, there's an obvious problem, which is that you can't very well intersect something with boundary, with a chain with boundary, and expect to have something well defined. So let me just draw you the problem. So let's have this one. We have this chain. And we have some intersection with this chain.
So the philosophy here is, you have to produce the scheme. So, and you have two sort of separate problems. One, you don't know how to count curves, and two, you don't really know how to derive the scheme, so you think that they're chances.
Yes. Yes. And when I'm trying to give this talk in a more impressive way, I explain that there are two famous problems of mathematics, one about you can't count these curves, one about you don't know what the skein relations are from, and then they, by some miracle, just cancel each other. Yeah. So it can happen in one parameter family that this intersection point just comes here and falls off. It's supposed to be intersection of the green and the white. So the green is four-dimensional, and the white is two-dimensional. You expect they meet each other at discrete points, and those points in the one parameter family can get to the boundary. Yeah, so I should say that this it seems from some it seems this four chain. What is it? It's like it's a homology class whose boundary is the Lagrangian. There's a very similar thing that appears in the physics literature called back reaction, where in the presence of such a brane, you modify the ambient symplectic form to something with a pole along the Lagrangian, and therefore its boundary is the delta function on the Lagrangian. That looks very much like this, but how the precise relationship is somewhat mysterious to me because of this next thing I'm going to say, which is related to something else which is mysterious, which is that in the Chern-Simons theory, in Witten's account or whatever, there is some problem with the self-linking number of knots, which causes some infinity, which he fixes in some way by adding framing, which I have never understood exactly what the principled, kind of principled thought process behind is. Anyway, so this here's something which goes wrong.
Wait, that issue arose from Melissa and Sheldon long ago, right? When they were so it was
that's maybe not. That's a different kind of framing.
No, it's the same kind of framing.
I think that's about the framing of the three manifold, not the framing of the knot. let me show you what this framing is, and then we can discuss the same or different. Okay, so this can come here and then fall off. Okay. So yeah, this phenomenon. And the problem with this is that I would count this one by A and this one by 1, which would be again a failure of invariance. And the cure to this problem is that I changed, so here I just said any Ford chain whose boundary is twice the Lagrangian, and now I make one additional requirement on this Ford chain, which is that I choose once and for all at the beginning of time some vector field on the Lagrangian. You can ask for it to be nowhere 0. You don't have to. You can allow it to have zeros, but let's ask it to be nowhere 0. And I demand that near the Lagrangian, this W is plus or minus the complex, I times the, like you rotate the vector field in the complex direction. So then it's going away from the Lagrangian. And what does that mean? That means that at this moment, because I have a holomorphic curve, which is intersecting J times the vector field, it had better also be tangent to the vector field. That's how complex curves work. So this red circle is tangent to the vector field at this moment. And conversely, only at, whenever the vector field is tangent to the curve, I must have an intersection with a Ford chain at the boundary. What does that mean? That means that here, as you would, if you do generic dimension count, you expect this. Here, this vector field is nowhere tangent to the curve, which means you can use it to define a framing. We use, so I wrote these skein relations. I didn't explain to you what on earth this meant. And what it means is that these skein relations are relations not for links, but for framed links, and framed means you choose a direction to push them off themselves everywhere. And this picture means that I push them off themselves. Whenever I draw them, you push them off themselves in the direction that comes at you, and then this is really different than this. This like twists around itself one more time. Okay, so very good. So yeah, so we see, so we use this kind of vector field to frame the link, the boundary of the curve. And then we see that as you undergo this process, you trade an A for a framing change, which is the third skein relation. I'm going to say it again. Okay. Yeah, so I'll first say again the problem. The problem is I count everyone by their intersection number with the Ford chain, and that can change in one parameter family. Now I demand that the Ford chain has a certain local behavior near the Lagrangian, and that local behavior is it goes in the direction J times the vector field. And what does that mean? That means that whenever the Ford chain intersects the holomorphic curve at the Lagrangian.
So this means that the vector field and the normal direction of the Ford chain together form a holomorphic.
Yes. And that means that if this normal direction of the Ford chain when the intersection point with the Ford chain goes to the boundary, then its tangent, this curve in the normal direction must be tangent to that the Ford chain. as the limit of an intersection point, but that, the curve is holomorphic, so its direction in the Lagrangian must therefore be tangent to the vector field. And so that means that at the same moment that I lose or gain a four-chain intersection, I pass through a failure of the vector field to frame the curve. And so the framing of the curve changes also by 1. And so that means that this process is exactly canceled by this skein relation. This says I trade A for a framing change. The boundary of no, only this vector field does. I choose a vector field. And you can ask, does it depend on the choice of the vector field? And the answer is no. But you prove it. I mean, you consider what happens in a it's the same argument. You consider what happens in a one-parameter family of vector fields. And what can happen in a one-parameter family of vector fields is exactly the same. Well, yeah, sure, you fix it, but then you can vary it later and then ask, did your answer depend? But the point is, you can't just vary the vector field. You have to vary the vector field and the four-chain. They're like one and the same kind of object. So maybe I write the formula for how I count the curves. It's Euler characteristic. I count the curves. So I count the curves, and I count them each by A to their intersection of the four-chain, Z to minus their Euler characteristic, and then the class of their boundary in the skein. Okay, and then the theorem with Tobias, of which the proof is like 100 pages of making this picture as precise, is that this count defines U an invariant.
If I just have Lagrangian in T star n, this guy has the 14 you want, or it doesn't? It doesn't, right?
Are you saying does one exist or does it?
Yeah, it's not.
Yeah, it exists. I don't. Is the
That's a nice. Double, like anybody could boundary.
In a cotangent bundle, if I take the zero section, take any vector field on it, take plus and minus j times it, and go to infinity. That's it. That's the four-chain.
That satisfies that boundary is twice n. Or
Yeah. Okay. Because like one direction would be just m, and then just take another one.
I thought I only
had. No. I mean, it's plus or minus. I mean, how to say? If I take a vector field.
The guy in T star n, right? It literally says.
If I take a vector field on M, I can take j times that vector field. That's some direction. And I can take minus j times that vector field. That's the other direction. And you can allow, okay, there's two things to say to that question. The first is that every 3 manifold admits a non-vanishing vector field, so you can take one if you want. And the second thing is that you can allow the vector field to have zeros, and then I have to tell you a slightly more complicated story. Okay, so that's the definition of this theory. And kind of a nice review for people who have been coming to my class. And now I want to explain about this this skein valued. Now let's discuss this this topological vertex. So first of all, what is the Lagrangian? Well, we go in C3, and in, 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 in the C3, we look at the sphere, the S5, and we take this kind of locus, that's e to the IA, e to the IB, e to the IC, with A plus B plus C equals theta, and call this lambda theta. And so there's like a circle worth of these things, they're tori. And any one of those tori, you can cone it off down to the origin. That gives you some cone. And you can smooth that cone in basically three ways. Corresponding to like the three coordinates. I don't want to say any more than that. You can smooth that cone in three ways. And so we take in C3, we take the Lagrangians, which correspond. So we take lambda 0, lambda 1/3, and lambda 2/3. We cone them all off, and we smooth them in the three different ways. So cone off and smooth in three different ways. So that's the Lagrangian on which we'll count holomorphic curves. And there's a
these are usual guys.
usual guys. Yeah, so the topology is of a solid torus. And let me, before I try and count on all three of them, let me briefly describe, so I described this at some length in the class, so sort of warm up, count on just one. Just the filling. Lambda 0. Because whatever I'm going to do is going to be a fancier version of that, so let me first do that. Okay, so to do this and to do later this kind of full vertex, we will study so the actual count is the count of objects in a zero-dimensional moduli space. And in the subject of Floer theory, the way you prove anything is you find a one-dimensional moduli space whose boundary teaches you something about the zero-dimensional moduli space you're interested in. That's how every argument in Floer theory works. So we will study a one-dimensional moduli space. And to get a one-dimensional moduli space, I mean, I just said all kind of counts of curves in the boundary in the Lagrangian is all zero-dimensional stuff because some index, some elliptic nonlinear PDE or whatever. And so the way you bump up the index is you allow the curves to go. So this is L, this is C3. You allow the curves to go to infinity in a certain controlled way. So it turns out that this Lagrangian has what is called a Rabe chord of index 1 at infinity. And maybe not so important what that is. Whatever it is it's the right kind of thing where you can, a Rabe chord is the kind of thing for which it makes sense to allow holomorphic curves to be asymptotic and still have a good kind of problem. Okay, so like whatever it is. I mean, there's some vector field on the contact manifold at infinity for which this is a trajectory. And then curves, the kind of, let's call it rho, Rabe chord rho. And then I'm going to write m rho for the moduli of curves with one boundary puncture, which is and the boundary puncture goes to infinity, asymptotic to rho. And whatever kind of, so this curve, it kind of goes up here, and then the inside does whatever it wants, and it has like boundary with boundary on L. Curves with boundary on L. With one boundary puncture asymptotic to rho. Yeah. There's a family, and you perturb it. I mean, the way I've written it, there's a like an S, not S5. There's an S. This theta parameter is the Rabe flow, and so the way I've written it, there's like an S2, an S1 times S1 of such chords, and you perturb it, and then after you perturb it, there's like there's like a, you take the smallest one is the index one, like the minimum, the one at the minimum is the index one. Okay, so yeah, so we studied. Yeah. Yeah.
So this report, I think of it as a flaw of Hamiltonian.
Yeah. So okay. What is it? Yeah, the wall is like vibrating. It's yeah. So okay, if you want to, maybe I'll maybe I'll go here and have like 5-minute crash course on contact geometry. If you have a contact manifold is a manifold W and a plane, hyperplane field C, which is whatever called maximally non-integrable. What that means is that there exists, so usually when you say contact manifold, you just give this plane field, but it means that locally, and we're going to always have globally, there exists a one form alpha, so that C is the kernel of alpha. And once you choose this one form, then there exists a unique vector field, which is called the Rabe vector field, R, so that such that R is in the kernel. So D alpha has like one thing in its kernel. So this means C is kernel alpha, and the maximally non-integrable condition means that alpha wedge D alpha to whatever power is volume. And there's a unique vector field R, so R is in the kernel of D alpha, and alpha of R is 1. And that thing's a Rabe vector field. It's called Rabe vector field. Or to discuss Hamiltonian in the contact setting, you need to choose this this kind of form. And once you choose that form, this is the thing which corresponds to Hamiltonian 1. Okay. So where are we? Yeah. So So anyway, there's this red chord. You can count curves asymptotic to it, and that's some moduli space. And the way you learn something from a one-dimensional moduli space is you study its boundary. What is the boundary of that moduli space? Boundary. So the boundary of the moduli space has two kinds of terms. So on the one hand, it's zero, right? It's zero in homology. When you count points of the boundary, it's zero. On the other hand, there are two kinds of terms in there. One is corresponds to these kind of breakings. So this is kind of breakings, like boundary breakings as before. Okay, and that's one part of the boundary. And the other part of the boundary comes from escape to infinity. So some topology or area can escape to infinity because I have this kind of non-compact picture.
Sorry, which boundary breaking are we?
So all these kind of skein relations I wrote, they correspond to the breaking of holomorphic curve at the boundary. That can still happen. It's boundaries along this Lagrangian, and it can still break along the boundary. But the other possibility is that some topology or area can run up to that red chord at infinity, and you have to you have to compactify the moduli space in some way, and discuss what the boundary strata with escape to infinity look like. That's the subject, which is called they call it symplectic field theory, and for some reason, it's some subject in symplectic geometry. And let me just tell you what those boundaries are. So the escape to infinity boundaries, they look like this. How to say? Someone wrote down a compactification of that moduli space, and I'm describing for you. Someone is Hofer and company, and they describe for you. So they gave a compactification. They described the strata of compactification, and I'm telling you what their description is. And this kind of strata in the compactification, they look like this. So I'm describing for you the codimension 1 strata. Then there will be higher codimension strata also. In this case, the one-dimensional moduli space. So we only have codimension 1 strata. And in general, what they look like is that, so you have this red chord row of index 1 here. How about yellow? Is red chord row of index 1 here. Then you consider holomorphic curve, which does whatever it wants in this this kind of region. Maybe it has some kind of closed part, has all of its boundaries on this orange thing. It's allowed to go down to rave chords on the boundary here, as long as these rave chords have index 0, and as long as we then continue it here by some similar picture. Whatever, it does whatever it wants. Okay, but it has to be a holomorphic curve. So the kind of boundary, things on the boundary are a pair of a holomorphic curve in S5 times R with boundary along this lambda 0 times R, asymptotic to rho, and then with some negative asymptotics to whatever index 0 rave chords, a pair of such a curve, and another curve with positive asymptotics of the same chords, and then whatever it wants in the inside. Yeah. So this is the general picture. But in this specific case, in general, it would be this. But in this specific case, there are no index 0 rate chords. And as a result, the boundary looks entirely like disconnected curves. So I should have said at the beginning, I count curves which I allow to be disconnected. The boundary, it consists entirely of disconnected curves, which look like this. Some piece upstairs and some piece downstairs. That's the boundary. So why is that useful? Well, the point is that what I discussed, since we're counting all curves in the skein, all this boundary, if I count this side and that side in the skein, all this boundary breakings are 0. So that means that the total count of escape to infinity is 0. But what is the total count of escape to infinity? The total count of escape to infinity is, it's this times this. And why times? Because I can combine anything that looks like this with anything that looks like this. There's no interaction. So if I call this total count A, and this total count, which is the count I want, psi, then A psi equals 0. And what does this equation mean? This psi, it lives in the skein of this Lagrangian, which is a solid torus. And this A, it lives in the skein of this kind of piece here, which is a torus times R. And the skein of the torus times R acts on the skein of the solid torus by sticking it on the outside. Okay, so under this action, what? You mean these 2 points? Yeah. So strictly speaking, the picture I drew, this would be a skein torus times R with 2 points on the side that is away from this thing, and this formula still makes sense and is true. But that's annoying because then that's not an algebra, and so I just close it up at infinity somewhere. You can leave it unclosed up. It's just somehow. For some purposes, it's important to leave it unclosed up. But so how does this help me? Well, now we're at something which is starting to look like the story I want to tell, where if I can derive A and prove that it determines psi, then I'm done. I've derived psi as well. Okay, and it turns out in this kind of business, A is much easier to compute than psi. So in this example, the way you find it is you look at the map from S5 to P2 to a triangle. This one is the moment map. And the Lagrangian, it maps, the Legendrian, lambda 0, it maps to this central point. And holomorphic curves in there, if you do some symplectic reduction, they become holomorphic curves in here. You project them to the moment map, they become lines. And there's 3 of them. And so you learn that A is going to have 3 terms. And if you look more carefully, what those 3 terms are okay, I'll draw it first with those 2 points. As Peng was saying, I'll draw it with those points, and then we'll close it up. What the boundaries so whatever the curves are, they trace something along this solid torus, this torus times R. They trace some trajectory, and what that trajectory is looks like this. So here's one of them. Here's one of them, and here's the last one. And if I want to close it up, which I do for some reason I do, and I this thing is the torus lambda 0, and these yellow x's they're not really they're just dots or whatever. These yellow dots, they are the two end points of this Rabe chord. That's 2 points on the torus. And then these orange curves, they're the projection to the torus of a curve in the torus times r, which is the boundary of one of these guys. And there's 3 of them because there are 3 such guys. Is this okay? Okay. Okay. So this A, it's the count of curves in this cylinder. It's the count of curves with endpoints with kind of one puncture, and that puncture stretches at this red chord. The boundary of such a curve should be an interval, maybe plus some disjoint circles a priori. Okay, so now what are those curves? Well, there are 3 of them. So, okay, how am I counting those curves? I take this S5 times R, I do some symplectic reduction along some S5 slice. That symplectic reduction is a map from S5 to P2. It's the usual quotient by the circle. I take the moment map of P2 down to a triangle. That lambda 0, it goes to the central point of that triangle. Holomorphic curves in P2 ending on that Lagrangian are well known. They correspond to these 3 trajectories downstairs. There's 3 of them. There's lots of ways to count those 3 curves. Okay, but there's 3 of them. And okay, and then I have to draw for you the boundaries of those curves. Eventually up here, and here there. Yeah. And this last bit here was just because you know, I want to deal with the skein without these points, so I just choose some way at infinity of closing them up. Make it a loop instead of an interval. It's not important, but I just do it. And so, well, it's important for maybe the next thing, which I'll say, which is that, okay, so what is that now? After I close it up, well, it's those 3 trajectories now, they look like the longitude, the meridian, and an unknot. And so A, I haven't, in this calculation, I haven't been keeping track of signs or somehow scalars or whatever, but A, what it is it's the unknot minus the meridian plus some, okay, plus or minus, depending on choices of spin structure and so on, but I'll put plus, and then plus some coefficient, which you can arrange to be A, times the longitude. And this formula, if you now specialize to the U1 and then you go to the classical limit, it's this usual 1 plus or minus x plus y, which is the mirror curve of that Lagrangian. Does that make sense? Yeah. Okay. So that's that is how you derive this A for this one Lagrangian case, and then you can turn it into combinatorics in various ways. One way is to use the fact that the skein of the solid torus is there's a known isomorphism of it to the tensor square of the ring of symmetric functions, and on that the skein of the torus times R acts as some like specialization of the elliptic Hall algebra action. There's some formulas for it, and then it's okay, so we can write this now in formulas. In those formulas, there's a in this space of symmetric functions, this meridian operator, it acts diagonalizably, and the eigenbasis is the Schur functions. Okay, so then, and this L acts as the raising operator. It acts as S1 box. So this whole thing turns into combinatorics, and the fact that this has a unique solution, which is the thing that it's supposed to be, is a special case of the argument I gave. It's unknown. It doesn't lower. So yeah, yeah. So you're asking how does the formula at the beginning specialize to this one? So there's a okay. So I'll go over here. So before, remember I had I could raise lambda 1 and lower, let's say, lambda 2. And if I have only one brane, then lambda 2 and lambda 3 are both empty. And so I only have one raising and no lowering. Yeah. Okay. So that was about one brane. And so now let me just say what, I won't say so much, but okay, let me say what is different about 3 branes. So it's harder in a meaningful way. So now I put 3 of those Lagrangians. I do the same thing. I count curves at infinity. And some of those curves are the ones I just counted.
Yeah. A is ambiguous, because it does depend on
depends on the choice of flow chain.
Yeah, and
That's the framing.
Yeah, exactly.
that you were talking about before.
Yeah.
But so it's related to the other one, but it's kind of a global framing choice, not a.
No,
I mean, anyway, that's what it is. There's actually 2 ambiguities which are related. There's the choice of this floor chain, and there's the choice of who you call longitude and meridian.
Yeah, no, that's the same choice.
Okay, maybe the same choice. Yeah. So I agree with you that is the choice in this Melissa, etc. Okay. Yeah. Okay. So yeah, now about 3 of them. So when there's 3 of them, again, you can look at what are the Rabe chords at infinity, and you find again these ones, but like 1 for each of the Lagrangians. But what's new is that there are now some Rabe chords of index 0 that go from one of the Legendrians to another one. And so now the new situation is that the bound. So now there's kind of like row 1, row 2, row 3, 1 for each of the Lagrangian, each of those Legendrians, and the new situation, and there's this M row 1, M row 2. They all behave. Each of these behaves the same way. And the new situation is this boundary. It looks like before there was like 3 disks, but now there are, in addition, 2 triangles. Okay, where the situation is that so this is always like this kind of row 1, and then along this boundary, it's on L1. Like the first one is Lagrangians. I guess it's calling L0. And then and on this one, it'll be on L1/3, and then back on L0. And there'll be a similar one with row 1, and it's on L0 here, and then it goes L2/3. You go to the other one. So there's some additional curves that you can count. Yeah, these three guys. And so now you can say, and these ones are similar. and now you can take 2 points of view on this. One is that instead of the problem with doing what I was going to do before is that this thing, it no longer annihilates just the count of interior curves. What it instead annihilates is the count of interior curves plus some, I mean, like it's like a vector where one entry is the count of interior curves, and the other one is a count of curves which are asymptotic to these index 0 wave chords. And that, so one thing which let me question, I don't know, physics or something, that other count, the count of things asymptotic, these index 0 wave chords, it is also a zero-dimensional count, and it has the right to have kind of a meaning in the subject. But it's a count that we can never in the past seriously consider. And so one thing you could try and do is you could try and use these recursion relations to determine not only the count of interior stuff, but also this other count of things asymptotic to 2 chords. And maybe in general, when you study the subject in some completely arbitrary situation, you need to do that. You need to build that vector of somehow counts asymptotic to like wave chords of index 0 and solve for it all at once. But in this particular case, a kind of miracle happens. And that miracle is that when you add these things in an appropriate way, these terms, you have to add these in an appropriate way and choose intelligent choices of capping paths at the bottom. These terms all cancel. So this is I do not understand what is the I don't have a precise understanding of what is the like principled reason for this miracle. Someday the understanding will be we build some skein valued version of what is called the symplectic field theory, which is some vector space, some differential, and the fact that this thing all cancels is a consequence of some homology group being 0. So like one day we'll have a principal explanation of it. We don't know. It just, we look at it and it cancels. And as a result, we get we find that certain appropriate linear combinations of these kind of terms must annihilate the count of curves entirely in the interior. And this linear combination, when we turn it into combinatorics, is the formula I wrote at the beginning. That's it. I think Tobias looked at your paper. I think Tobias looked at your paper. Do you have this thing? This
Yeah, I mean, it must be happening exactly what.
It must be in there somewhere. Yeah, it must be in there somewhere. But it's,
which is precisely that you can trade the action